Namaste and a very warm welcome to yet another lecture on mathematical foundations for machine learning. In the last couple of classes we have been looking at the ideas of eigenvalues and eigenvectors, and we defined eigenvectors to be the invariant direction for a linear map, and the only effect of the map on the vector is just to scale. Such vectors we call them as invariant vectors, are basically the eigen vectors for the transformation T, and the transformation T is essentially captured in terms of your matrix, say matrix A, and we said that if you want to find out the eigenvectors, first of all we need to find the scaling factors, for which we said that okay, the matrix must be singular because you are looking for a non-zero vector which gets scaled by this transformation. So, we said that the matrix has to be singular. So, we said determinant of A minus lambda I must be equal to 0, because we said Ax equal to lambda x, and you bring it to the other side, you say it is A minus lambda I times x is equal to 0, and we are looking for a non-zero vector out there. So, what we want is determinant of A minus lambda I is equal to 0, and we call that to be the characteristic equation of the matrix A, and we also found the roots of this characteristic equation is going to be the eigenvalues, and then you substitute the eigenvalues in that expression Ax equal to lambda x, you start collecting the eigenvectors corresponding to the eigenvalues that you have had. Now, when we wound up the last class, we had a question like what are the applications of these eigenvalues and eigenvectors, so where do we see them? And we also had another interesting question, said like what is it to diagonalize a matrix A. So, these are the questions that we had in the last class, and we will try to go in a direction where we will be answering these few questions, and we will also look at a couple of properties of the eigenvectors, and then we will look at some applications and so on. Okay, so there we go. Let us look at, we were basically looking at let us say a transformation T, and the associated matrix is, let us say the matrix associated with this, let us call that as A. So, A is the matrix representation of T, the linear transformation. The linear transformation T, and we were looking at finding out the eigenvalues and eigenvectors for this particular matrix. We said that okay, I want to look at A u is equal to lambda u for some scalar lambda for some real lambda. So, I will take it as real scalar. So, I will say for some real number lambda. So, now what we said is A minus lambda I times u, because that is a scalar, I can't subtract this scalar from a matrix. So, I take this as A minus lambda I times u is equal to the 0 vector, is equal to the 0 vector, and we said that to find lambda, solve determinant of A minus lambda I is equal to 0, obtain the values of lambda, and then substitute in this equation, get the value of u for each of those lambda, that is what we said. Now, there are a few questions that we want to ask. Suppose A is an n by n matrix, let us say suppose A n by n matrix is such that the eigenvalues are repeated, the eigenvalues are, we will do this. Number 1, we will take eigenvalues are case 1, where we say unique case 2 we are going to say the eigenvalues are repeated. We will say instead of unique we will say distinct, that is a better word to use. So, we say that the eigenvalues are distinct. Case 2 where the eigenvalues are repeated, that means you may have some repeated roots for the characteristic equation that you have. So, this basically was called the characteristic equation of A. Right. So, we can have distinct roots, we can have repeated roots. Now, what happens in the case of distinct roots and what happens in the case of repeated roots? So, let us just look at this, and there is a third case where this can throw out a surprise, where the eigenvalues are complex. These things can happen, right. You have distinct roots, you have repeated roots, and you have complex roots, and we will look at where do we encounter these cases, and then we will try to address I mean what could be done or what happens in each of these cases. For all these things what we will do is we will just take examples of some 2 by 2 matrix and try to understand from the idea of 2 by 2 matrix, where we are not able to understand this 2 by 2 matrix or there is some issue with this 2 by 2 matrix. Let us go to a 3 by 3 matrix and try to understand what happens there. Okay, so let us take the eigenvalues are distinct. So, that means I have this characteristic polynomial which is basically this one. So, we have the characteristic polynomial. So, we have a n by n, and we look at determinant of, from here where we look at the characteristic polynomial. So, we look at determinant of a minus lambda I is equal to 0. So, this is going to be a degree n polynomial. And therefore, we must have n roots of the polynomial. Right. Now, the question comes like 1, are the roots, are the n roots distinct? Two, are the n roots repeated? Are there repeated roots among the n roots? Among the n roots, and the third question, are the roots complex? 3, are the roots complex? So, let us take an example in each of these cases and see what happens. So, the first example that we are going to look at is the following. Example 1, consider our matrix A, which is basically 2 1 1 2. This is the matrix that we want to have, and what we are going to say is, look, the matrix A is associated with some linear transformation T, and that T transformation, linear transformation T, is captured in terms of this matrix A, which is 2 1 1 2. Now, if you try to do this determinant of A minus lambda I, we already saw it in the previous case on the previous class, determinant of A minus lambda is equal to 0. We get 2 minus lambda 1 1 2 minus lambda. The determinant of this matrix, the determinant of this matrix is 0, which implies we get lambda is equal to 3 and lambda is equal to 1 if you solve this we did in the last class. So, we have lambda is equal to 3 and lambda is equal to 1 to be the root. So, what we see here is this first example says that, look, the eigenvalues are distinct, eigenvalues are distinct, right. Now, each of these distinct eigenvalues are associated with eigenvectors. So, what we are going to say is we are going to say that, look, lambda is equal to 3 or lambda 1 is equal to 3 and is associated this corresponding eigenvector, let me call this as EV1, which is basically 1 1. This was done in the last class, so I am not doing it again. I have lambda 2 is equal to 1, the corresponding eigenvector here was 1 minus 1, right. These are the two eigenvectors that we have for this matrix A. The eigen values are distinct, and what can we say about these two eigenvectors? Something interesting that comes out here. If you look at the two eigenvectors, 1 1 is in some direction and 1 minus 1 is in a different direction. Therefore, what do we see? We see that the eigenvectors corresponding to distinct eigenvalues are basically linearly independent. So, we are going to make a statement here, we are going to say that look, we are going to say eigenvectors corresponding to distinct eigenvalues are linearly independent. Now, that is a tall statement that we make. We want to prove this, like can we prove that this is indeed true? We have seen this, maybe who knows, in a different case it could be they are linearly dependent vectors, we really do not know, but we just want to prove that if this actually works. This is a statement that we can, is this the statement that we can make across all the linear transformations that we have, meaning the linear maps that we have. So, the linear maps or the matrices A square matrices such that if you have eigenvalues to be distinct, does it necessarily mean the eigenvectors are linearly independent. So, this is a question that we have. So, let us just take a quick proof of this. The proof seems to it does not involve much of a labor to prove it. I will prove it in the 2 by 2 case, and you can extend it by, I mean, for the case of any n by n matrix you can use induction and prove it. So, let us just look at this simple case where we have let T be a linear map or a linear transformation from, let us say, R 2 to R 2. From R 2 to R 2, and let A be the matrix representation of T. A be the matrix representation of T. That means A is going to be a 2 by 2 real matrix. Right, we are going to say A is a 2 by 2 real matrix. Now, what are we going to do? So, what we want to do is we want to prove that, let us look at, let lambda 1 and lambda 2 be the distinct eigenvalues of A. And let u and v be the eigenvectors, their corresponding eigenvectors. That means u is associated with the eigenvalue lambda 1 and v is the eigenvector associated with lambda 2. So, corresponding eigen vectors, right. That means lambda 1 u and lambda 2 v are eigenvalue eigenvectors pairs. Let me say this EV pairs, eigenvalue eigenvector pairs. So, we are going to say this. Now what do we want to prove? We want to prove that u and v are linearly independent. So what is the claim? We claim that u and v are linearly independent. Right, we need to say so what does that mean? We can choose. So so what we have, this implies alpha 1 u plus alpha 2 v is equal to 0 vector, right, alpha 1 u plus alpha 2, this is the claim, we need to prove this claim. So alpha 1 u plus alpha 2 v is equal to 0 implies alpha 1 is equal to 0, alpha 2 is equal to 0, this is what we want to prove. So now what we do is we will just take alpha 1 u plus alpha 2 v is equal to 0 and then let us try to apply the transformation on this. Okay. So what is the transformation applied on alpha 1 u plus alpha 2 v is basically the transformation applied on the 0 vector. We are going to look at basically the linear combination which is going to give me the 0 vector on the right hand side, a linear combination of the eigenvectors u and v which will give me the 0 vector. We already know that a linear transformation T is going to map 0 vector to the 0 vector. So I have, suppose if I have a combination alpha 1 u plus alpha 2 v is equal to 0 vector. So it is going to map it to the 0 vector which is going to be again the 0 vector itself. Now by the property of our linear combinations I can also write this as alpha 1 the transformation applied on u plus alpha 2 the transformation applied on v is going to give me the 0 vector. Now it is interesting to note here that the transformation when applied on u is the eigenvector we said associated with the eigenvalue lambda 1. So when the transformation T is applied on u the effect is just to scale, the effect of the transformation on u is basically to just scale. So it is alpha 1 lambda 1 u plus alpha 2 lambda 2 v is equal to 0, this is what we have. So let us call this as, let us say we will call this as equation 2 and we will call this guy as equation 1. So equation 2 says that alpha 1 lambda 1 u plus alpha 2 lambda 2 v is equal to 0 and equation 1 basically looks at the linear combination of the two vectors which is going to give me the 0 vector. So now what am I going to do? I am going to multiply equation 1, let us say multiply equation 1 by lambda 1 throughout, that means both LHS and RHS is going to multiply lambda 1. So what are we going to have? We have lambda 1 alpha 1 u plus lambda 2 alpha 2 v is equal to, oh sorry, this is the whole thing, okay. So this is going to be lambda 1. So I am going to multiply that. So I am going to have lambda 1 alpha 2 v, that is equal to be equal to the lambda 1 scaling the 0 vector which is going to give me 0 vector itself. So what do we have? We have lambda 1 alpha 1 u plus lambda 1 alpha 2 v is equal to the 0 vector. Now this, let me call this as equation 3 and then we will recall equation 2 here. Equation 2 was basically this, lambda 1 alpha 1 u plus lambda 2 alpha 2 v was equal to 0. This was basically the effect of the linear transformation applied on the linear combination. So now what I do is I am going to do equation 3 minus equation 2, that is going to knock off these two guys. So what I have lambda 1 minus lambda 2 into v, of course the scalar alpha 2 is there, that is going to give me the 0 vector. Now what is interesting here, if you see that alpha 2 into lambda 1 minus lambda 2 is equal to 0 implies, if you look at this, note that lambda 1 and lambda 2 are distinct, implies lambda 1 minus lambda 2 is not equal to the 0 scalar 0, and also V is a non-zero vector, non-zero eigenvector or non-zero vector, because our eigenvectors are non-zero vectors. So, we have non-zero vector. Therefore, the only way by which this equation, let us call this a star, by this so this equation star can become 0 only if alpha 2 is 0. I will say can become the 0, I mean the right hand side is 0 vector on RHS is by making alpha 2 is equal to 0. If alpha 2 is 0, then we already know that alpha 1 u plus alpha 2 v is equal to the 0 vector, implies alpha 1 into u vector is equal to the 0 vector. U is a non-zero vector, therefore, alpha 1 must be 0. Therefore, what we see is alpha 1 is equal to 0, alpha 2 is equal to 0, and what we have is alpha 1 u 1 plus alpha 2 u 2 is equal to the 0 vector, sorry, alpha 1 u plus alpha 2 v is equal to 0 vector is possible only by making alpha 0, only when alpha 1 is equal to alpha 2 is equal to scalar 0. That means the vectors u and v are linearly independent. Right. So, what is the conclusion now? We are going to say that eigenvector corresponding to eigenvectors corresponding to distinct eigenvalues or eigenvectors associated with distinct eigenvalues are linearly independent. Right. So, we have already proved the claim that we had, right. The second example that we took, the second case that we were looking at was when the eigenvalues are repeated. Right. So, let us take this transformation T associated with this matrix which is given by let us say 1 1 0 1. In this case we have lambda minus 1 the whole squared is equal to 0 as the characteristic equation, which means lambda is equal to 1 twice. That means that this is a repeated root. Since these two the two eigenvalues are repeated, what we see is in this case there is only one eigenvector associated with lambda is equal to 1. So, the eigenvector is basically 1 0. Though you have two eigenvalues, since both of them are the same, in this case you find that there is only one eigenvector. However, you have certain exceptions. Suppose if you take the identity matrix, identity transformation, the matrix A will be identity matrix 1 0 0 1, every vector in R2 is going to be an eigenvector for that. So, there are certain exceptions. Now, what we do is we look at this case where we see that the eigenvector is just 1 0. Now, there are two definitions that I want to bring in here, and post that we will look at something interesting. So, I want to bring in two definitions. One is the definition of what is called as algebraic multiplicity. Algebraic multiplicity, right. So, what is this algebraic multiplicity? We are going to define this as the number of times, this is denoted as A m, the number of times an eigenvalue is repeated is called the algebraic multiplicity. Associated with that particular eigenvalue, say lambda. And we also have what is called as geometric multiplicity, we will just check now. So, the second definition that we want to look at is geometric multiplicity. Which I am going to call it as GM. This is nothing but the number of eigenvectors let us say linearly independent eigenvectors associated with a specific eigenvalue or associated with a particular eigenvalue, say lambda. You call this as the geometric multiplicity. For example, let us look at this. When we had the matrix A, which was 2 1 1 2, the eigenvalues were lambda 1 is equal to 3 and lambda 2 is equal to 1. The corresponding eigenvector was 1 1 and the corresponding eigenvector here was 1 minus 1. So, in this case we say that the algebraic multiplicity of lambda 1 is equal to 3 is equal to 1, algebraic multiplicity of lambda 2 is equal to 1 is equal to exactly 1, and the geometric multiplicity of lambda is equal to 3 of lambda 1 is equal to 3. There is only one linearly independent eigenvector associated with this, which is going to be 1. The geometric multiplicity of lambda 2 is equal to 1 is also equal to 1 because you just have one eigenvector which is 1 minus 1. Now, in the second example that we took, example 2 that we took, where we had A to be this 1 1 0 1, we had lambda 1 is equal to 1 repeated twice. And the corresponding eigenvector was just 1 0. Therefore, what are we going to say? We are going to say that look, the algebraic multiplicity of lambda is equal to 1 is 2, whereas the geometric multiplicity of lambda 1 is equal to 1 is 1, because there is only one linearly independent eigenvector associated with this. So, what we have is we always have this note, the geometric multiplicity is always less than or equal to algebraic multiplicity for each lambda, right. Now, what happens when the geometric multiplicity is less than the algebraic multiplicity? We say that the corresponding eigenvalue is deficient. So, let us make this definition. We say that if the geometric multiplicity of a specific eigenvalue is less than the algebraic multiplicity, we say that the corresponding eigenvalue is deficient. Now, let us take example 3. We will come back to this idea of geometric multiplicity and algebraic multiplicity in a different context in some time now, or probably we will look at that in the next lecture. Now, what we will do is we will just quickly look at the third example where I have complex eigenvalue. Suppose I take this transformation corresponding to rotation by 90 degrees where I have 0 minus 1 1 0. Now, determinant of a minus lambda I is equal to 0 implies lambda squared plus 1 is equal to 0, which implies lambda is equal to plus or minus I, complex number. This is basically rotation by 90 degrees counterclockwise. It is not surprising to see that rotation matrix has no real eigenvalues in this case, rotation by 90 degrees. For that matter, rotation by except rotation by 0, 180 and 360, all the other rotation by any other angle is going to have this problem. The reason being, the purpose of rotation itself is to reorient the input vector, which means the transformation whatever vector you give is going to reorient it. Therefore, there is going to be no fixed direction for rotation transformation. Now, what is the problem here? We ended up seeing that the complex eigenvalues, right, the eigenvalues are complex in this case, though the matrix is real, we end up getting complex eigenvalues, right. Okay. Now, what is the purpose of looking at all these things? I mean, that is exactly where we need to look at. We get into the idea of diagonalization of a matrix. Let us say look at this diagonalization of matrix A. Right. So, what is it to diagonalize a matrix A, and what is the effect of diagonalizing the matrix A? Why do we want to do it? How are we going to do it? These are some questions that we have, which we will answer in the next lecture. In this lecture, what we have done is we have basically looked at the properties of eigenvalues and eigenvectors. We just said that distinct eigenvalues of a particular matrix, the eigenvectors corresponding to them are linearly independent, and then we said that okay, the characteristic equation of the matrix A could be such that the roots are distinct, the roots going to be repeated, or roots could be complex. And when we also brought in the definition of geometric multiplicity and algebraic multiplicity here, saying that the number of times an eigenvalue repeats is basically what you call as the algebraic multiplicity, and then the geometric multiplicity is basically the number of linearly independent vectors associated with a given eigenvalue. We looked at that, and we also looked at certain examples where we said that okay, you had distinct eigenvalues, you had repeated eigenvalues, and you just found that there is going to be only one eigenvector associated with the eigenvalue despite the root being repeated, and in that case we call the specific eigenvalue to be deficient. Now, these deficient fellows are going to make our life a bit complicated, which we will see when we do this diagonalization. So, the content for the next class would be on diagonalization of the matrix. It comes out with a lot of interesting applications. This diagonalization basically helps you do something, a few things very in a very interesting manner. We will look at this, and we will also see what could this guy matrix with eigenvalue which is deficient, what kind of a problems can he pose. So, that is what we are going to look at in the next class. Thank you.